To determine the appropriate size inverse time circuit breaker for a feeder supplying multiple motors, you will need to perform several calculations based on the National Electrical Code, specifically Article 430. First, determine the full load current for each motor. For a 75 horsepower, 480 volt, three-phase motor, the full load current is 96 amps. Next, apply an intermittent duty cycle factor. Since the 75 horsepower motor operates on a 15-minute intermittent duty cycle, apply a factor of 0.85 as per Article 430.22. A. Multiply the full load current of 96 amps by 0.85, which results in an adjusted full load current of 81.6 amps. Now, apply the inverse time circuit breaker factor. For inverse time circuit breakers, apply a factor of 2.5 as per Article 430.52. Multiply the adjusted full load current of 81.6 amps by 2.5, which yields a circuit breaker current of 204 amps. Next, calculate the total feeder current by adding the circuit breaker current of the 75 horsepower motor to the full load currents of all other motors connected to the feeder. The circuit breaker current for the 75 horsepower motor is 204 amps. The full load current for the 15 horsepower motor is 21 amps. The full load current for each of the two 10 horsepower motors is 14 amps. Add these currents together: 204 amps plus 21 amps plus 14 amps plus 14 amps, which equals 253 amps. Finally, select the appropriate inverse time circuit breaker size. According to Article 240, the feeder overcurrent protection should not exceed 250 amps. Therefore, a 250 amp inverse time circuit breaker is appropriate for this application. In summary, firstly, find the full load current of the 75 horsepower motor. Secondly, adjust for the intermittent duty cycle. Thirdly, calculate the circuit breaker current. Fourthly, determine the total feeder current. And fifthly, select the appropriate breaker size ensuring it does not exceed the maximum allowed by Article 240. This method ensures proper protection for the motors and the feeder complying with NEC standards. Now let's delve deeper into each of these steps to provide a more comprehensive understanding. Starting with determining the full load current, it's crucial to use the correct tables in the National Electrical Code NEC. For a 480 volt, three-phase motor, you'll typically refer to NEC Table 430.250. This table provides the full load currents for various horsepower ratings. Ensure you are using the correct voltage and phase configuration when selecting the full load current. After obtaining the full load current from the table, the next step involves adjusting for the intermittent duty cycle. Article 430.22. E addresses motor applications with intermittent duty. This section allows for a reduction in the conductor ampacity based on the duty cycle. In this case, a 15-minute intermittent duty cycle allows for a factor of 0.85 to be applied to the full load current. This reduction accounts for the fact that the motor is not running continuously at its full load. The inverse time circuit breaker factor is a critical aspect of motor protection. Article 430.52 specifies the maximum allowable overcurrent protection for motors. For inverse time circuit breakers, this value is typically 250% of the motor's full load current after adjustments for duty cycle. This higher percentage is allowed because motors draw significantly inrush inrush current when starting. The inverse time characteristic of the breaker allows for this inrush current to pass without tripping, while still providing protection against sustained overloads. Calculating the total feeder current involves summing the contributions from all motors connected to the feeder. Remember to use the adjusted full load current for the 75 horsepower motor, which already accounts for the intermittent duty cycle. For the other motors, use the full load currents as obtained from NEC Table 430.250. Adding these currents together provides the total current that the feeder conductors and overcurrent protection must be capable of handling. Selecting the appropriate inverse time circuit breaker size involves considering the calculated feeder current and the requirements of Article 240. Article 240 provides the general requirements for overcurrent protection. In this case, the overcurrent protection device, which is the circuit breaker, must be sized such that it protects the feeder conductors from overload. The NEC typically requires that the overcurrent protection device be sized no greater than the ampacity of the conductors it is protecting. However, in motor circuits, there are specific allowances for using larger overcurrent protection devices to accommodate motor starting currents. In this scenario, with a calculated feeder current of 253 amps, selecting a 250 amp circuit breaker is appropriate because Article 240 dictates that the next lower standard size breaker should be selected if the calculated value does not correspond to a standard breaker size. It's important to note that the conductor ampacity must also be sufficient to carry the calculated feeder current. Conductors are selected based on their ampacity, which is the maximum current they can carry continuously without exceeding their temperature rating. NEC Table 310.16 provides ampacity ratings for various conductor sizes and insulation types. Ensure that the conductors selected for the feeder have an ampacity of at least 253 amps in this case, and that the circuit breaker is protecting those conductors according to NEC guidelines. In addition to these calculations, consider the voltage drop in the feeder conductors. Excessive voltage drop can negatively impact motor performance and can even damage equipment. The NEC recommends limiting voltage drop to no more than 5% from the source to the farthest motor. Use voltage drop calculators or software to estimate the voltage drop in the feeder conductors and increase the conductor size if necessary to reduce the voltage drop to an acceptable level. Grounding is also a critical aspect of motor installations. Ensure that the motors and the feeder are properly grounded in accordance with NEC Article 250. Grounding provides a low impedance path for fault current, which helps to quickly trip the overcurrent protection device and minimize the risk of electric shock. Equipment grounding conductors should be sized according to NEC Table 250.122. Furthermore, consider the short circuit current rating of the circuit breaker. The circuit breaker must be able to safely interrupt the maximum available short circuit current at the point of installation. Obtain the short circuit current value from the utility company or perform a short circuit study to determine the available fault current. Select the circuit breaker with an interrupting rating that is equal to or greater than the available short circuit current. Coordination studies are also important in multi-motor applications. A coordination study ensures that the overcurrent protection devices are coordinated such that a fault on one motor circuit will only trip the breaker for that circuit without interrupting power to other critical loads. This involves selecting circuit breakers with appropriate time current characteristics and performing calculations to verify that the breakers will operate selectively. In addition to the NEC requirements, consider any local codes or regulations that may apply to the motor installation. Local codes may have additional requirements or restrictions that must be followed. Always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations. Motor control centers, or MCCs, are often used in multi-motor applications to provide centralized control and protection for the motors. MCC contain individual motor starters, overcurrent protection devices, and control components for each motor. When using an MCC, ensure that the MCC is properly rated for the voltage, current, and short-circuit current requirements of the installation. Also, verify that the motor starters and overcurrent protection devices within the MCC are properly sized for the motors they are serving. Variable frequency drives, or VFDs, are increasingly used to control motor speed and improve energy efficiency. When using a VFD, it is important to consider the harmonic currents that the VFD can generate. Harmonic currents can cause overheating of conductors and equipment, as well as interference with other electronic devices. To mitigate harmonic currents, use line reactors or harmonic filters. Also, ensure that the conductors and overcurrent protection devices are properly sized to handle the harmonic currents. Power factor correction capacitors are sometimes used to improve the power factor of motor circuits. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased current flow, higher energy losses, and reduced system capacity. Power factor correction capacitors can improve the power factor by reducing the reactive current. However, it is important to properly size and apply power factor correction capacitors to avoid overcorrection, which can also cause problems. Surge protection devices, or SPDs, are used to protect motors and other electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD diverts surge current away from sensitive equipment, preventing damage. SPD should be installed at the service entrance and at the motor location. Ground fault protection is also an important consideration in motor circuits. Ground fault protection detects ground faults, which are unintentional connections between a phase conductor and ground. Ground faults can cause electric shock and can also damage equipment. Ground fault protection devices, such as ground fault circuit interrupters (GFCIs) or ground fault relays, can be used to detect ground faults and trip the circuit breaker. Arc flash hazard analysis is becoming increasingly important in electrical safety. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause severe burns, injuries, and even death. An arc flash hazard analysis determines the potential arc flash hazard at various locations in the electrical system. The results of the analysis are used to determine the appropriate personal protective equipment (PPE) that workers must wear when working on or near energized electrical equipment. Lockout-tagout, or LOTO, procedures are essential for ensuring electrical safety during maintenance or repair work. LOTO procedures involve disconnecting and isolating electrical equipment from its power source and placing a lock and tag on the disconnecting means to prevent accidental re-energization. Only authorized personnel should be allowed to perform LOTO procedures. Regular inspections and maintenance are crucial for ensuring the continued safe and reliable operation of motor circuits. Inspections should include visual checks of conductors, connections, and equipment for signs of damage or deterioration. Maintenance should include tightening connections, cleaning equipment, and testing overcurrent protection devices. Keeping accurate records of inspections and maintenance activities is also important. Training is essential for all personnel who work on or near electrical equipment. Training should cover electrical safety, proper work practices, and the use of personal protective equipment. Only qualified and trained personnel should be allowed to work on electrical equipment. Motor nameplate information is essential for proper motor selection, installation, and protection. The motor nameplate provides information such as the motor's horsepower rating, voltage, full load current, speed, and installation class. Always refer to the motor nameplates when performing calculations or selecting equipment. Motor efficiency is an important consideration for energy savings. High-efficiency motors consume less energy than standard efficiency motors. When selecting a motor, consider the motor's efficiency rating and choose a high-efficiency motor if possible. Energy audits can help to identify opportunities to improve energy efficiency in motor systems. An energy audit involves analyzing the energy consumption of motor systems and identifying areas where energy can be saved. Implementing energy-saving measures can reduce energy costs and improve the sustainability of operations. Soft starters are often used to reduce the inrush current during motor starting. Soft starters gradually increase the voltage applied to the motor, reducing the inrush current and minimizing stress on the electrical system. Soft starters can also improve motor starting performance and reduce mechanical shock to driven equipment. Overload relays are used to protect motors from overheating due to overload conditions. Overload relays monitor the motor current and trip the motor starter if the current exceeds a preset value for a specified time period. Overload relays should be sized according to the motor's full load current. Short circuit protection is provided by fuses or circuit breakers. Short circuit protection devices must be able to quickly interrupt high fault currents to prevent damage to equipment and minimize the risk of electrical hazards. Short circuit protection devices should be sized according to the motor's full load current and the available short circuit current. Undervoltage protection is used to protect motors from damage due to undervoltage conditions. Under-voltage protection devices monitor the voltage and trip the motor starter if the voltage drops below a preset value. Under-voltage protection can prevent motors from restarting automatically after a power outage, which can be dangerous. Phase loss protection is used to protect three-phase motors from damage due to phase loss conditions. Phase loss occurs when one of the three phases of the power supply is lost. Phase loss can cause the motor to overheat and can also damage driven equipment. Phase loss protection devices monitor the voltage or current in each phase and trip the motor starter if a phase loss is detected. Motor monitoring systems can provide valuable information about motor performance and condition. Motor monitoring systems can measure parameters such as motor current, voltage, temperature, and vibration. This information can be used to detect potential problems early and prevent motor failures. Predictive maintenance techniques can be used to anticipate motor failures and schedule maintenance before failures occur. Predictive maintenance techniques include vibration analysis, infrared thermography, and oil analysis. These techniques can help to extend motor life and reduce downtime. Remote monitoring and control systems can be used to monitor and control motors from a remote location. Remote monitoring and control systems can provide real-time information about motor performance and can also be used to start and stop motors remotely. These systems can be particularly useful for applications where motors are located in remote or hazardous areas. Motor enclosures are used to protect motors from the environment. Motor enclosures are available in a variety of types, including open drip-proof, totally enclosed fan-cooled, and explosion-proof. The type of enclosure required depends on the environment in which the motor will be installed. Explosion-proof motors are required for applications where flammable gases or vapors may be present. Explosion-proof motors are designed to contain an internal explosion without igniting the surrounding atmosphere. Motor bearings are critical components that support the motor shaft. Motor bearings must be properly lubricated to ensure smooth operation and long life. The type of lubricant required depends on the motor's speed, load, and operating temperature. Motor cooling is essential for preventing overheating. Motors are typically cooled by air or liquid. Air-cooled motors use a fan to circulate air over the motor windings. Liquid-cooled motors use a liquid coolant to absorb heat from the motor windings. Motor vibration can be an indicator of a problem. Excessive motor vibration can cause damage to the motor and driven equipment. Vibration analysis can be used to identify the source of the vibration and correct the problem. Motor noise can also be an indicator of a problem. Unusual motor noise can be caused by wound bearings, loose parts, or electrical problems. Motor testing is essential for verifying motor performance and identifying potential problems. Motor testing can include insulation resistance testing, winding resistance testing, and surge testing. Motor repair should be performed by qualified personnel. Motor repair can include replacing bearings, rewinding the motor, and repairing damaged components. After repairing a motor, it should be thoroughly tested to ensure that it is operating properly. Motor replacement may be necessary if a motor is severely damaged or worn out. When replacing a motor, it is important to select a motor with the same horsepower rating, voltage, and frame size as the original motor. Proper motor installation is essential for ensuring reliable operation. Motor installation should include proper alignment, grounding, and wiring. Motor commissioning is the process of verifying that a motor is properly installed and operating correctly. Motor commissioning should include testing the motor's performance and verifying that all safety devices are functioning properly. Motor documentation is essential for maintaining a motor system. Motor documentation should include motor nameplate information, wiring diagrams, and maintenance records. Motor management programs can help to improve motor system reliability and reduce maintenance costs. Motor management programs can include predictive maintenance, motor monitoring, and energy efficiency measures. These best practices will ensure your motor and the related circuit breaker are well understood, specified, and maintained.